Ouais, un test de son. Ok, nickel. 1, 2, 1, 2. Ok, bah si tu marches, on est bon. On y va, ok. So, hello everybody. We will finish this day of presentation by the plenary of Corentin. We mentioned during the General Assembly yesterday that it would be nice to have a bit more overview of what the industry is doing in bioacoustic, and Corentin will present what Artesis is doing with bioacoustic for the industry. So, Corentin, floor is yours.
Thank you. First of all, thank you for inviting me and giving me the opportunity to introduce our solutions and what we do. So my name is Corentin Troussard. I'm sales manager at RTCs. And the presentation I will give today will try to give you an overview about what are the new technologies in the industry, more from an application point of view than a purely scientific. Actually, I'm not an acoustician myself, so I would not be able to get into the details. Just before we get to the first use case, a quick introduction about our company. So RTCs is a manufacturer of underwater equipment, so both underwater recording system and we also do underwater autonomous vehicles. We are part of a wider group with another company who is specialized in distribution of various solutions, and a third company that is specialized in survey, so providing service to industry. Speaking about RTCs only, we are a French company based in Brittany. We were created in 2010. We are now 70 employees, with approximately half of them in the R&D office. So we still have a quite strong R&D DNA. We are a worldwide footprint with a presence in more than 80 countries. Maybe with direct customers, but also partners, so on all continents. And we have a 24/7 dedication to our customers, thanks to two offices. So our main office is in Brittany, and we also have a small office in Singapore to address the Asian market, mainly due to the time difference. So we developed 4 different ranges of product. 2 are more defense focused and 2 are science industry focused. I will just quickly explain the first on the top left. It's anti-submarine warfare. So that's basically autonomous vehicles that helps navies to train to submarine detection. We also have a wide range of solutions for mine countermeasures, so trying to find mines on the seabed and identify it closely. Autonomous underwater vehicles, mainly dedicated to seabed survey, so we have sonar systems, so that's not bioacoustics, but still run on acoustics to get 2D imagery of the seabed. And finally, the passive acoustic monitoring, which is our main topic today. A short list of reference for you, mainly on the top right, science and environment. That's just a non-exhaustive list of the research institutes we are used to work with, some of the most reputed in the world. So the first use case I wanted to introduce today is real-time acoustic monitoring in coastal and offshore construction for immediate decision making. So the product I will introduce on that topic is a buoy we developed, which is called Ruby AI. From a technical point of view, it's a system which has 4 synchronized channels for passive acoustic monitoring. We have also an option to add water quality sensors. So typically, in the use case of offshore wind farm, it might be interesting for the industrials to have at the same time acoustics and some parameters like turbidity for checking the sediment movement during the construction. We have possibility to have real-time monitoring and alerts. So may it be noise level calculation or marine mammals detection. Going too fast. We have some wireless means to transmit the data in real time. So depending on the distance you want to reach and the coverage you have, we have Wi-Fi, radio, and satellite. And the system is fully autonomous thanks to big solar panels. Basically, that's the picture. So we have in the spar all the electronics, antennas on the top, obviously, and the hydrophones are going under the water. So what is the main problematics in offshore construction? This is a catchy picture we want to avoid. It's a non-thing that the noise produced underwater is very harmful for marine life. And offshore construction is one of the biggest threats to the marine mammals. So more and more countries have set some regulations to monitor the noise underwater to protect this marine life. So that graph here is based on the German regulation, but more or less every country have similar regulations. Basically, it implies to have a monitoring point at 750 meters from the noise source. And we have embedded processing of the noise calculated. We can process to have sound exposure level, sound pressure level, etc., third octave band, a wide range of different parameters that we can send in live by radio or by satellite. And we developed software for the users that you see on the top left. So if you are an acoustician, we have all the data that are displayed. You can also download everything on an Excel tab. If the operator is not an acoustician, which is often the case in the industrial applications, we have this very simple color system. If you make too much noise, it goes red. And this is a quick demonstration of what you see on the screen. So here we are on pause, and some data will come in. So we receive some data every 5 seconds, and you see everything updating. We also developed this web platform to display all the data. So here we have only noise levels and status info, but we can also display some marine mammals detection that I will show in the next slides. This is just a short video, a testimony from one of our customers who has been using the system in the Saint-Brieuc offshore wind farm. So it's in the northwest of France. For the French people in the room, probably you know it has been quite a mess with fishermen protesting against the installation of the wind farm. Basically, they were afraid that the installation of the farm will be in their fishing area. And some studies have been requested to check the impact of the work on the species. And after these studies, we also had the same kind of monitoring during the installation.
Cette bouée est une bouée de mesure acoustique sous-marine qui nous permet d'enregistrer tous les sons émis sous l'océan dans une large gamme de fréquences et qui nous permet également d'obtenir toutes les 10 minutes une mesure des niveaux sonores émis par les travaux de forage en baie de Saint-Brieuc. La bouée est équipée d'un hydrophone. Un hydrophone, c'est un capteur acoustique sous-marin. Et donc ce capteur est placé à 15 mètres de profondeur, ce qui nous permet de nous éloigner de la surface. les données sont enregistrées en continu sur la bouée. Une valeur moyenne des niveaux sonores mesurés est envoyée par iridium toutes les 10 minutes, ce qui nous permet en fait de suivre les niveaux émis par les travaux de forage en continu pendant la durée du suivi. Toutes les 3 semaines, on récupère la totalité des données brutes et ce qui nous permet en fait ensuite de faire des analyses plus fines sur les niveaux sonores émis et puis les caractéristiques de tous les sons qu'on a pu enregistrer. Ce qu'on voit ici, c'est le niveau sonore qui est mesuré au niveau de la bouée acoustique, donc qui est à 500 mètres du bateau de travaux. Et les variations qu'on voit sont liées aux variations du courant de marée. Donc on a une oscillation en fait qui suit les courants de marée avec une augmentation au moment où la marée est la plus forte. Et ça génère en fait des bruits d'écoulement.
Ah oui, mais c'est pas ce qu'on voyait l'an dernier, du coup, quand on avait les bouées en dérive.
Exactement. Quand on utilisait notre système de bouée à la dérive, comme la bouée dérive avec le courant, on n'avait pas en fait ces fluctuations du niveau de la marée sur les enregistrements.
Finalement, ce qui est là, c'est plutôt dû à la marée et le bruit qu'on mesure, il faut prendre sans le bruit de marée, donc c'est plutôt le bruit qui est ici à chaque fois?
Oui, exactement. On se place à l'étal. Donc on voit en fait qu'on a un étal toutes les 6 heures. On se place à l'étal pour avoir une mesure précise du niveau de bruit des travaux. L'ajout ici, là, c'est lié en fait aux conditions environnementales.
Ok.
So I'm not sure you all had time to read the last sentence on the screen. Basically, it mentions that the systems was able to monitor and control that the noise was way below the limit. So that's obviously interesting for the project and for the marine life in the area. It has also been very interesting for the industrials for communication purposes. To help getting consent from the local communities. So that's something that is quite interesting and important when talking about industries and the new offshore solutions, etc. Because there are still a lot of people that are a bit reluctant to install this kind of offshore wind farms. So by doing this kind of measures, we can convince them that it's not that harmful. Second feature, which is very interesting in the buoy, is marine mammals detection algorithms. So this is something that is provided by our partner Sensi, which is a French company based in Grenoble. Actually, I think they were sponsor of the conference last year, so maybe some of you already know them. So they developed a system based on a deep neural network. I will definitely not go into the details. You know it way better than me. Just to say that it's been trained on different 5 training incrementation on years and years of raw data acquired in very different conditions from all around the world. And all the parameters you see here, distance of detections for misty sets, about 20 kilometers, definite clicks for 1.5 kilometers, and definite wheel cells around 1 kilometers, with very satisfying confidence level, 93% for vocalizations, and 95.6 for clicks. So that's obviously based on a specific study, on a specific area. You probably know that when going to a different site, you need to train again the algorithm. But still, I think it's a very encouraging results. Here are the reference of the paper on which these results are based. So as of today, the system is able to detect approximately 15 different species that you see here on the screen, so different kind of whales and dolphins. And what is the output for users? So as soon as the detection is done, you can program the system to send an alert to the web server. So you will receive this kind of data on the right of the screen, where you will see the classification, the timestamp of the detection, And you also receive the spectrogram with an audio sample that you can play to make sure this is a real detection or not. And we also have a confidence level, so you can configure the system to only send alerts upon a certain level of confidence. And these alerts can be sent by email or SMS. You can also download everything on an Excel tab. The algorithm is pretty much configurable, so the users have the ability to configure the detection thresholds, the sound to noise ratio. You can also configure a count for receiving an alert. So basically, when you are on the field and you have a lot of dolphin around, for instance, probably you don't want to receive an alert every second for the detection. So you can configure either a delay or a number of alerts before receiving a message. And this is just how it works from a user point of view. So this is on the web platform where you have your different buoys. You see the detections. That's status info about the buoy. So you see where is the buoy, how much battery it has, how much storage capacity. Again, different kind of noise level informations. And the detections with the spectrograms and possibility to play the sound. And what we'll see, it's a bit slow. There is possibility to download an automatically generated report with a summary of the different alerts. So for the marine mammal observers on site, I believe it's a big save of time. Obviously, you still are able to check all the raw data to validate the detections. But with this kind of reports, you can go straight to the interesting times and save a lot of time in the data processing. And in terms of real applications, so last year we've been involved in that project, which is the monitoring of the installation of the coastal Virginia offshore wind farm. So that's a wind farm based on off the east coast of the US. That's actually, as of today, the biggest wind farm in operation. So the contractors was DEME, which is one of the biggest industrial in the offshore industry, and they had 176 turbines to install, roughly providing 2.6 gigawatts. So that's equivalent of the energy for 660,000 homes. So that's not negligible. And the objective of the project here was to maintain 10 kilometers mitigation zone around the wind farm, especially to protect North Atlantic rat whales. So we had 7 of the buoys monitoring 24/7 around the park to monitor the presence of the mammals. And basically, as soon as there is a detection, the contractors had to stop the work, waiting for the whale to move away. So as a feedback after the project, it confirmed that several actions need to be carried out to reduce the false positive. In the first weeks of the project, we had a lot of false positive in the algorithms, mainly because the training on site was a bit too light. We only had 1 week of raw data on site to train the algorithm again. So we had to do new training again during the project. And also there is an importance to fine-tune the algorithm parameter depending on the different detection we receive. Data transmission rate is also very important. When talking to the scientific community, I'm used to hear that you want the data, all the data at any time. When you are speaking to an industrial working offshore, communicating with satellite data, every message has a cost. So at the beginning of the project, we indeed sent every detection, even with a low level of confidence. And at the end of the first month, the bill for iRhythm communication was so high that we decided to reduce our criteria. And for us, for industrial, what is interesting is that project confirmed that the solar panels allow to have a full autonomy, which also reduce the need for maintenance and reduce the cost for the boat site. And we also faced a very big storm, which is very confident for us to make sure that the buoy has sustained these hard conditions. So as a result for this kind of equipment, long delay calculations and manual detection allows the contractors to check the compliance to local regulations. It also allows to implement the necessary mitigation as soon as possible. So that's quite interesting both for marine life, but also for the contractors, because this allows them to reduce the work interaction time, and considering the number of boats and people on site, it's a huge save of money, and on some opportunities also for them to avoid the big fines. And for surveyors, which is probably more interesting for you in the room, I think it allows you to save time, because it helps to focus on the more interesting data, rather than checking a full day of raw data. Obviously, you need to punctually check the raw data, because you can't trust 100% the algorithms. But I think after a few weeks of project, it's really helpful. And what next? We want to implement a system of localization. So basically, we will have different buoys with a time synchronization, and comparing the level of noise of the detection, we expect to be able to accurately localize the animal and confirm if the animal is inside or outside the exclusion zone. So that was the first use case, and then I have a second one, which is quite different. I mentioned that we manufacture underwater autonomous vehicles. We actually have a project for combining acoustics and robotics. And this is the CMAS project, so it means continuous environmental monitoring at sea. And the objective of that project is to provide a self-powered platform for long-term surveillance and preventive maintenance. Basically, the system is composed of two main elements. So we have the surface platform with solar panels in that section here. We also have all the storage of data inside. Embedded sensors can be deployed off the board of the platform. We have the wireless communication on site. And what you see below here is what we call a LARS, for a launch and recovery system, for the AUV that you see below. And that AUV will have the possibility to stop on the seabed or on surface to stop the engine and be able to acquire acoustic data. So that's based on one of our systems, which is the Nemo Sense AUV. Just to give you a few key features, it's an AUV which can go down to 300 meters with up to 20 hours of endurance. It's only 10-12 kilograms depending on the sensor package, So it's very light and very easy to deploy and recover. So what do we do on that project with the AUV? We came from the fact that the main issue when trying to recording with a vehicle motorized is engine noise, which is giving a lot of parasite noise to the acoustic data. So we had to find a way to stop the engine to allow to record in a quiet period of time. So the first thing we had in mind was to stop the engine during navigation to let the system glide and be able to acquire the data. The problem is that with AUV, so it's a torpedo-like vehicle, when you do that, there is a lot of impact on the navigation, and for other reasons, we have a lot of safety, so both are not really compatible, and the AUV will basically go in abort mission mode and go back to surface. So what we did on the project was to implement an adjustable ballast that you see on the front of the vehicle, with a pump that is able to include water or air depending on what you want to do. And that's some picture of our test. So you see this is the initial condition, and the AUV will basically go up to surface and finish in that position here. So we have antenna on surface to transmit the data, and the acoustic hydrophone underwater to acquire the data. This is not bioacoustic, definitely, but quite interesting as well. We also developed a long baseline, the water communication, for the AUV to be able to dock into the launcher recovery system. So that's based on different kind of acoustic communication protocols. And the interest is to dock the AUV for battery recharging and data transfer. We also expect to have a future development of oil housing, so the AUV can be protected from the seawater. Basically, the big interest of this project is to extend the area of coverage of a single system. So you can expect to have up to 30 kilometers of navigation with the AUVs. So you can cover a very large area. The battery autonomy of the surface station allows to recharge the AUV. So we have a very low need for maintenance. So you save a lot of back and forth both travels. And the applications for this kind of systems are very wide, from marine biology to defense. So in conclusion, with the advance of this different system, obviously the protecting our environment has become a very essential thing. Finally approved by most of the people. It's been a long time to come here, and we realized that permanent presence at sea is essential now for an exhaustive monitoring. So we have needs for system with a lot of autonomy. These technical advances also make it possible to have more inbound data at a controlled cost. But what do we do with this data? We need to process it. So artificial intelligence is a very helpful tool to monitor on the very important data. And collaboration between industry and scientific community is very crucial for us to tailor the different algorithms we include, and also to be able to push the industry into what you need to enhance your different studies. So that was for the use case, and very quickly to finish, I just want to have a quick overview of the different systems we offer in the passive acoustic range. So we have this system, which is a single channel recorder. So for that one, we really focused on low consumption, so there is no embedded processing. It only records the data. But the low consumption allows to have up to 6 months of continuous recording. And we have started the development for a multiple channel version of that one that will be pretty configurable for the users to have up to 16 channels. And you see that's a very compact system that can be easily deployed by divers. This is somehow the big brother with 4 synchronized channels, very large bandwidth, and many options available, like inclusion of a GPS, of addition of third-party sensors, also possibility to stream the data directly to a computer. So this device, for instance, is compatible with PalmGuard. PalmGuard is a well-known software for those who are not used to underwater acoustic. It's a software for data processing and different kind of mammals detections. We have the Remy, which is a very small buoy. It's 35-40 kilograms. So it's pretty easy to deploy it from a small boat by only 2 people. Same thing for synchronized channels, transmission of data by radio or Wi-Fi, and 20 days of autonomy with this one. And then we have the Ruby Boy, which is kind of an intermediate between the one I showed in the use case and the one on the previous slide. So that one is bigger and can sustain AVC up to 685. So it's pretty convenient for offshore monitoring with an autonomy of up to 40 days. And that's all for me. Thank you. For those who are interested, obviously you can reach me. There is also a few catalogs and brochures in the other room, so feel free to get it.
Thank you so much. Do we have any question?
Hi, thank you. That was really interesting. I have 3 questions. The first one, and it might be that I missed some information. I'm a little bit distracted. Is there a chance we could get those slides to read up on some of the details of your products?
Yes, I think so. I will share it with the organization, and
you guys just email it or something.
Yeah.
That would be amazing. Second question, for your detector, it has a really good precision.
Yes.
Do you know where it was trained?
Yes.
Like
most of the papers I show in the next slides were based on studies in the Gulf of St. Lawrence in Canada.
Okay, pretty cool. And then I just had an idea about your autonomous vehicle. You said that you have the issue with the engine when it's on.
Yes.
I was thinking about those headphones that have this noise cancelling. I don't know anything about that. I was just wondering, because you know the frequency of your engine, and like it's such a predictable sound. Did you think about if there's any filter to really get rid of that engine noise?
That's something we have been thinking about. 2 reasons actually why we did not implement that. First one is because the noise from the engine is actually so high that even with reduction, we still hear it, and it's not good for data quality. And at the same time, this kind of processing also consume a lot of power, so that reduce the autonomy of the vehicle. So yeah, not
makes a lot of sense. Thank you.
Hi, thank you for the good talk. It was really informative. I'm trained as a marine mammal observer, so I'm going to be out in the field in these kind of environments with construction and wind farms, also like seismic surveys. So I also have 3 questions. I'm really sorry. But the first one is, why I haven't considered using the real-time odontoseat call classification algorithm in PAMGuard instead of like the current classification method you have, which has like less species, I guess, on it.
Main reason is again consumption.
Okay.
We are not able to implement PimeGuard directly into our systems, so that would have meant having a computer on board, streaming the data to that computer, and then again streaming the data to wireless. So that's something that consumes a lot of energy, and that's a key factor in the system.
I also wanted to know if your company or a company you work with are developing any noise mitigation equipment to go alongside your monitoring devices, like, you know, like a bubble net around pile driving or...
Yeah, we don't. We are often meant to discuss with these people because obviously we are in the same project. Mm-hmm. But actually we don't really team up with them as we are selling to the same people, more or less. So we are on the same level, but with no real bridge between us.
Yeah, that's fair enough. And this might be a question, but can any of your underwater robots basically service stationary monitoring devices, or is that not something that would be useful?
Could you explain what you mean by service?
I mean, like, if the memory runs out on the device, can you go and change the card, or is it always broadcasting the information to like, the satellite?
Our system can only navigate on a straight line and stop without any interaction with what's around. To do what you're speaking about, probably ROV would be more appropriate. That's ROV means remotely operated system, and that's the kind of system with a cable going to the surface and an operator directly commanding it.
Okay, thank you.
Is there any other question?
Thank you. And you said that the buoy were relevant to sea state 5. What are the risks in higher sea states?
Alors, well, actually, that level is given by our buoy supplier himself, and the risk is to have the antennas basically damaged. You can also have the mooring line. Sorry? Yes, basically snapping. Yeah. So the buoy may drift. We have some safety systems, like when the buoy drifts too much, we receive an alert with the GPS position, but that means a lot of maintenance work, etc. So that's a bit risky.
Okay, thank you.
And now it's time for the mean question. So the really simple one you've got with only one hydrophone, like self-contained units, is a little bit like a sound trap, right?
Yes, it is.
I think a lot of us are familiar with sound trap, how much they cost and their abilities. Could you compare the two models?
To give you a fair answer, I think we are slightly more expensive, but our capabilities are slightly above. So basically, in terms of data resolution, we have a possibility for 24 bits. If I'm not wrong, I think they only do 16. We have, I think, a bit more storage capabilities. We can sample at higher frequency. We have more battery autonomy. So that's pretty much the same device, but I would say everything is a bit more on our side.
So what's the highest sampling frequency you're?
We can sample up to 512.
Cool. Thank you.
Welcome.
Thank you very much for the presentation. Your devices present the noise level that can be recorded, especially the voice, as I remember. Like it was presented in the video, as far as I remember. How are they calibrated? And is there any dispersion through time when you deploy them for a long time?
Our system, the recording part is calibrated in-house based on electronical calibration table. So we provide the reports and all the value. And the hydrophones are also calibrated by our suppliers. So depending on the suppliers, some do it on standard, some other ask for an additional fee. So indeed it's calibrated, and regarding the drift, from our experience, actually it's quite small. So for noise level calculation, where the value are very high, the need for recalibration is very low. For more accurate application like monitoring marine life, etc., we recommend recalibration every 2 years.
Thank you.
Hello, thank you for your presentation. I've got a question about the detection distance for whales and dolphinids. How did you calculate those detection distances?
I think it's based on the studies I show in the next page, and basically we had one system with the algorithm at one point, and a lot of other systems all around. So by post-processing the data, Sensi was able to calculate the position of the mammal, and assess at what point we lose the signal.
Thank you.
Any other question? Well, thank you very much. It was a very nice presentation. Thank you.